Hello everyone. Good morning or good afternoon based on where you're from. My name is Michel Ram and I'm a developer here at Scientific Volume Imaging. And I will be showing you the new Array Detector quality control tool that will be released soon with Huygens 22.10. If at any point during this webinar you have questions, you can send them to us via email to info@svi.nl. And with that little bit of information out of the way, let's start this webinar on Array Detector, deconvolution, and quality control. We have done a webinar on Array Detector microscopy in June before, where we gave information about the theory of Array Detector image acquisition, the deconvolution of Array Detector images in Huygens, and the PSF distillation for many Array Detector layouts, including the ArrayScan2 Shepard summed images. If at some point things become unclear, feel free to re-watch that webinar on our website on svi.nl/webinars. Let's now first walk through a small recap of the most important bits of information, like the key differences between Array Detector microscopy and regular confocal microscopy. Regular confocal microscopy uses a single photo detector to capture light from the first Array disk. This light passes through a pinhole to block out the out-of-focus light which you have with wide field microscopy. However, for array detection microscopy, the light is not blocked by a pinhole. Rather, each of the separate detectors acts as a small shifted pinhole, collecting a fragment of the first Array disk of the emission beam. Which means they independently, each detector has a sharper image. However, it's less signal than a regular confocal microscope would have. The fact that we sample the Array disk at different parts of the beam with many detectors means that you will get a data set that has as many images as you have detectors, and they will appear visibly shifted with respect to each other. In other words, you contain more information about the spatial distribution of the emitted light. And before we can actually do analysis, we need to process these many detector images to one single super resolution image. To do that, we need to shift back the outer detector's images to overlap with the central detector's image, and to do this correctly, a good alignment of the microscope during acquisition is crucial. What I always try to encourage our customers to do is to visualize the raw data from the images by opening them in any 2D or 3D visualization tool of choice in Huygens Essential or Professional. You can view the information stored in the individual detectors by going to the detector slider in each of the visualization options within Huygens. On the 2D slicer, it's a separate tab on the bottom left, and in, for example, the 3D SFP renderer, it's an option on the top right. Now, what we see here is not a time series of a moving fibroblast cell. Rather, it is a single array detector image with the information over all 32 detectors displayed one after another. Here we visually see the differences in intensity of the central detector with respect to the outer detectors. Note that a shift in the data is also visible. Take a quick moment to look at the shadows projected onto the background to really see this effect. As I mentioned before, the differences in the positions of each detector also means that the image will appear shifted with respect to each other. But by shifting back the separate detector images to overlap and then sum them appropriately, this results in an image with a higher resolution and better contrast. And by using deconvolution on top of that, we can get results of up to 70-90 nanometer resolution. In order to shift the images back, the positional information of the detectors is important, and a proper alignment of the detectors is necessary to get the best image out of the Array Detector deconvolution results in Huygens. Huygens supports many different detector layouts. However, you do not necessarily need a commercial array detector microscope, since we also support custom layouts. Let's now open Huygens and see if we can work with some array detector images sent to us by some of our customers. Here we have an image of a neuron captured with an array scan which has 32 detectors. We can see this by going to the Statistics tab on the top right. And here we see the number of detectors is 32. If we look at the histogram, we can visualize the intensity information in channel 0 or channel 1. And we can also select to see them both. However, with an array detector image, you have also got the option to view only the intensities of the central detector in detector 0, or maybe one of the outer detectors in detector 26. And this can give you insight in the alignment of your microscope, and especially if it's done, if the alignment is proper. And you can check this by seeing if there are significant amounts of intensity collected by all the detectors. And you can do this by cycling through the histogram in the main window. Another way is to open a 2D slicer, for instance, and visually inspect the data. Let's now check this image slice by slice. And this is the data from the central detector, which is shown on the top left here. So we can also create a sum projection, which shows you all of the slices on top of each other, summed. And if we now go to the detector tab on the bottom left, we can visualize the differences in intensities in each of the detectors. You can really see the shift between each detector, each image acquired by each detector. So all of the options I just showed you to visualize the intensities have been possible since Huygens version 18.10. However, in the upcoming release, we will show you the Array Detector quality control window that will allow you to see this information more straightforward after opening the tool. This tool is available from the Deconvolution wizard, and by clicking through the pre-processing stages in this step-by-step wizard, you arrive at the Array Detector Analyzer stage. And by clicking this window, you will open, clicking this button, you will open a new window that shows you the intensity distribution of each channel across the detection plane. This is displayed with a color scheme where low intensities are black, purple, and blue, and higher intensities are shown in yellow, orange, and red, like our false color scheme in the slicer. For this array scan image, the alignment was done properly, and you can see that the central detector has the most intensity. And as you move towards the outer detectors, the intensity gets less and less. The number inside each circle represents the scaled intensity with respect to the central detector. In the case that the central detector is not the detector with the most light captured, then you can also change it to be colored and normalized with respect to the detector with the maximum intensity. You can do that right here on the right. For this image, there is no difference. Below the image, there is a table that lists the intensity per detector, where detector 0 is in the center and detectors 1 through 6 are the first ring, and so forth. You can choose to visualize these intensities in false color mode or in grayscale by selecting one of the radio buttons here. You can also choose to visualize the intensities of all the channels in the image, or selectively disable or enable the channels of your choosing. If I click on channel 1, it will be disabled and I will still see a proper alignment. If I now click on this arrow to the right, I will disable channel 0 and enable channel 1 at the same time. And note that the intensities of the yellow fluorophores are not distributed over the entire array. The outer detectors did not capture as much light for the yellow channel as it did for the red channel. I will now enable both channels again. So You can export this information from the top menu bar by clicking File, Save Export, and Export Intensity Table. You can also export the visualization of the intensities in the color mode of your choosing from this same menu option by clicking Export Displayed Image. There is also a second tab in this window for the shifts. This contains information about the positional information of the detector array. For CZI files, this is measured when opening the images and saved in the microscopic parameters of the image. This can also be measured from the shifts in the projected images of each detector, which is then fitted to a template. So if we click Calculate, we see now that there are red numbers displayed on top of the current microscopic parameter positions of the detector array. These are the measured shifts. We can fit those measured shifts, and this will show you the Array Detector template, which will be used to deconvolve the image. So the positions that we store in our microscopic parameter window are derived from these parameters: the rotation, the spacing, and also the aspect ratio. By clicking Fit, it will find the best of these three parameters, including a mirroring check that best suits the data in your image. If we now click Apply Detector Layout, it will store them in the microscopic parameters of the image, which is visualized in green in this visualization. For Array scan images, this is already done after opening the files. After verifying the intensities and shifts, we can now close this window and continue with deconvolution as normal. So let's go back to the slides and take a look at a couple examples I wanted to show. So whether you're processing in Huygens or other software, make sure to always check your results with the original raw data. Here we can see an image of an array detector microscope that has not been processed correctly. So on the right hand side we see the raw data, and by comparing it to this result we clearly see that each measured pixel was interpreted like a spherical blob after processing. And something might have gone wrong when setting parameters for deconvolution or processing, but even in the regions with more intensities it also seems off and not resembling any biological structures. So make sure you try out different parameters when deconvolving. There are tools in Huygens that can measure the background and estimate the signal to noise to distinguish the signal of your biological samples from the background. And when applied correctly, this can show you much more detail in the resulting images. So instead of the blobbier images on the left, you can get a really good image to do your analysis on. And now let's go back to Huygens Professional again, where I have another example ready. So here we have another image sent to us by one of our customers, and from visualizing you can see very faint details of structures, but after deconvolution this does not get resolved properly, and by using our new Array Detector quality control tool we can see what might have gone wrong with the acquisition of this image. So the deconvolution wizard takes quite a while to load on this large image, but we can click on the Array Detector Analyzer tool again, and it will then open. And here we can really see that the intensities in all of the detectors are not really as we expect them to be. So the central detector is not the detector with the highest intensity. If we click on Normalize the intensity to the maximum detector, we see that this detector on the left has the most intensity with respect to all of them. And we can see in this table here on the bottom that the data does not match up with our expectations. And we can save this for maybe something went wrong when aligning the microscope, the lasers with the detector array. So this unfortunately cannot be properly processed. So this can really give you great insight after your measurements on what to do with your images. And unfortunately, in this case, this had to be re-imaged again. So I have a couple more slides left, and with that, I would like to go back to that. So far, I've shown examples for array detector images from the ArrayScan 1. However, we also support ArrayScan 2, and they have severely reduced their file size by not saving the raw data of each 32 detectors, but they are shifting the detectors back and then summing the detector data in each ring to a separate ring detector, and this is called the Shepherd summed image. And the positional information is then already resolved for these files. However, you can still use the Array Detector quality control tool to show the intensity of each summed ring detector. And next, we also have a great example from one of our customers with an image acquired by an ArrayScan in fast mode. And here only the 3 central columns of 16 detectors were used to acquire 4 lines simultaneously. And we also show the intensity, distributions, and positional information for this layout. So if you want to try out Huygens with these new options, they will be released on the 22.10 version later this month. And if you really want to try it out, you can contact us. So that was the webinar, and if you have any more questions, feel free to ask them and send them to us via email at info@svi.nl. And with that, I would like to close this webinar off, and until next time.